At Rescue Education, we have the best explanation every time. I'm Dr. B, and I'm going to help you easily and rapidly learn organic chemistry. If you like the video, you'll love my book. Learn more about it at rescueedu.com or hear more about it at the end of the video. The second semester book comes out in fall 2020. Let's talk about molecular orbital theory and its most important result for organic chemistry. sp3, sp2, and sp hybridization of orbitals. First, let's review some very basic molecular orbital theory and some examples of simple overlap of orbitals to make bonds. Lewis bonding theory fails to predict many aspects of structure and reactivity in organic chemistry. Molecular orbital theory, MO theory for short, is much more accurate. It's a very sophisticated mathematical approach which relies on quantum mechanics. Quantum mechanics takes into account the wave nature of electrons. We won't talk at all about how it works. We'll just use the results that apply to organic chemistry. We use MO theory to predict where electrons reside in atoms or molecules with a certain probability, for instance 95%. If we know where electrons in a particular molecule are, we know its structure. In organic chemistry, reactions occur when electrons move to make or break bonds. If we accurately know where electrons reside in the bonds of molecules, we can both understand and predict reactivity. For this reason, MO theory is very important, and you should spend some time learning it. Molecular orbitals are derived from the overlap of atomic orbitals, AO for short. So we need to start with learning about atomic orbitals. An atomic orbital is the area around an atom where an electron is likely to be. The size of the orbital is defined by the probability that a particular electron resides there, for instance with 95% probability. An atom can have several atomic orbitals of increasing energy. Each orbital houses a maximum of 2 electrons. The atomic orbitals we need to worry about in organic chemistry are shown here in increasing energy. The 1s orbital is the lowest energy orbital. It's spherically shaped and holds 2 electrons. The 2s orbital is next highest in energy. It too is spherically shaped and holds 2 electrons, but it's bigger than the 1s. It has an area right around the nucleus called a node, where the electrons are not allowed to be. You could say the area of the node is taken up by the 1s electrons, so it's unavailable. The next highest energy orbitals are the 2p orbitals. They are 3 dumbbell-shaped orbitals, which each hold 2 electrons for a total of 6 electrons. They are orthogonal to each other, that is, they are at right angles to each other, and so are called 2px, 2py, and 2pz. They are degenerate, which means they all have the same energy. An electron can go into any one of them equally as well. The 2p orbitals have a node right at the nucleus. Orbitals are grouped into shells. The first shell consists of the 1s orbital and can have a maximum of 2 electrons. The second shell consists of the 2s and 2p orbitals for a maximum of 8 electrons, which we can call an octet. Let's briefly review the rules to derive the ground state electronic configurations of the atoms important in organic chemistry. The Aufbau rule says you need to fill the lowest energy orbital first. The Pauli exclusion rule says each atomic orbital can only house 2 electrons. It also says they must be spin paired, 1 spin up and 1 spin down. Finally, Hund's rule says if you have degenerate orbitals, like the 2p orbitals, you need to give each orbital 1 electron before you pair them up. It's energetically costly to pair electrons, so you don't do it until all degenerate orbitals are filled. Here are the ground state electronic configurations of several important atoms. Hydrogen has only one electron, so it must go in the 1s orbital. Helium has two electrons, which both go in the 1s orbital. Helium has a filled first shell, so it's stable as the atom. It does not want to form any bonds. Carbon has 6 electrons. After the 1s orbital is filled, the 2s orbital is filled. Then the last 2 electrons go into separate 2p orbitals. Carbon atom is not stable because it does not have a filled second shell. It will want to bond to get a full octet. Nitrogen has one more electron than carbon, which goes into the last 2p orbital. Oxygen, with one more electron, has to put that electron into a partially filled p orbital. Fluorine has yet one more electron, which goes into another partially filled orbital. Finally, neon has a complete octet in the second shell and is stable as the atom. It does not want to bond with other atoms. Bonding happens when partially filled atomic orbitals overlap to form molecular orbitals. The simplest bond is between 2 hydrogen atoms. Each atom has one electron in a 1s orbital. The 2 atomic orbitals overlap. The new molecular orbital contains 2 electrons. In the molecular orbital, the vast majority of the electron density is directly between the 2 nuclei. This type of bond is called a sigma bond, which we signify by this Greek letter. A sigma bond is a strong bond because the interaction between the 2 electrons and the 2 nuclei is maximized. The overall bond formation is highly exothermic, which means it's highly favorable. The actual number, 436 kilojoules per mole, is very large. The reason it's so favorable is because you are forming a very stable molecule from 2 unstable atoms. Intuitively, you can say that molecular hydrogen is much more stable because the bonding electrons are now interacting with 2 nuclei. Another example of simple overlap is formation of fluorine molecule from the atoms. In this case, 2 partially filled 2p atomic orbitals overlap to form a new molecular orbital. You will notice that one lobe of the fluorine is shaded and the other is unshaded. This indicates the phase of each lobe and has to do with the wave nature of the orbital. To overlap and make a bond, the lobes of the atomic orbitals must have the same phase. The resultant bond is a sigma bond with electron density concentrated directly between the 2 nuclei. Sadly, carbon does not have such simple bonding. To explain this, let's talk about sp3 hybridization and the bonding in methane and ethane. Experimentally, it is known that methane has 4 exactly identical bonds. All the bond lengths are exactly 1.09 angstroms, and all the bond angles are exactly 109.5 degrees. If you look at the original electronic configuration of carbon, it has only 2 unpaired electrons, which suggests that carbon should only be able to form 2 bonds. We need to use a process called hybridization to derive the correct atomic orbitals for bonding in the carbon of methane. This is a mathematical mixing of 1 2s orbital and 3 2p orbitals to form 4 identical sp3 orbitals. Here are the rules for hybridization. The first rule is that the total number of orbitals mixed must equal the total number of hybrid orbitals. Here we take 4 orbitals, and we get 4. The next rule is that the hybrid orbitals are degenerate, that is, they have exactly the same energy. They contain exactly the proportions of the original orbitals. The sp3 orbital contains 1 part s and 3 parts p. Once the hybrid orbitals are formed, The electrons are distributed to them using Hund's rule, which means you fill each degenerate orbital with one electron before you start pairing them. Rule 4 says that hybrid orbitals arrange around the carbon to minimize electron repulsion. Rule 5 is that the new hybrid orbitals are intermediate in energy between the original atomic orbitals. Finally, you overlap the hybrid atomic orbitals with the atomic orbitals of other atoms to form bonds. Let's go through the entire process starting with the original electronic configuration of atomic carbon. We take one 2s and all three 2p orbitals and we hybridize. That is, we mix them together. Then we get out 4 new sp3 hybridized orbitals. We take 4 orbitals and we must get 4 orbitals. Each orbital is identical and has 25% s and 75% p character. The sp3 orbitals are all of equal energy, that is, they are degenerate. Notice their energy is intermediate between the 2s and the 2p orbitals they came from. Finally, we distribute the 4 electrons in the second shell to each sp3 orbital according to Hund's rule. We don't want to pair electrons until all degenerate orbitals are filled with 1 electron. A hybrid sp3 orbital looks like an uneven dumbbell shape because we've added the 1s orbital only to the side of a p orbital with the correct phase. We often simplify and omit the tiny lobe of the sp3 orbital. Each of the 4 sp3 orbitals contains an electron, so they array themselves in a tetrahedron to keep the electrons as far apart from each other as possible. That is, to minimize electron repulsion. Finally, each sp3 orbital overlaps with 4 hydrogen atomic orbitals to yield methane. All of the CH bonds are sigma bonds. I like to use this first representation for the orbitals because you can still see the shape of the contributing atomic orbitals. But you can also show the shape of the actual molecular orbitals, like in this second drawing. In the molecule ethane, the carbon-carbon single bond is made by overlap of 2 sp3 carbons. This is a sigma bond because virtually all of the electron density resides directly between the 2 carbon nuclei. This is a strong bond because it's a sigma bond. Most carbon-carbon single bonds are made by overlap of 2 sp3 carbons. One last point is that there is free rotation around the CC bond of ethane. This means that at room temperature, the CC bond is constantly rotating and the hydrogens are always moving relative to each other. Most CC single bonds have this free rotation. We'll talk about the implications of this in Unit 4 when we talk about conformations. How can you tell if an atom is sp3 hybridized? The rule is that any carbon, oxygen, or nitrogen with any combination of 4 bonded atoms and/or lone pairs of electrons will be sp3 hybridized. In this first molecule, each carbon has 4 bonds, that is, they are all tetravalent and are all sp3 hybridized. In fact, all of the other tetravalent carbons are sp3 hybridized. We don't have time to derive the hybridized orbitals of oxygen and nitrogen, but the rule applies to them too. Oxygen, with 2 bonds and 2 lone pairs, is also sp3 hybridized because it has 4 groups around the atom. Nitrogen, with 3 bonds and 1 lone pair, is also sp3 hybridized. The simple carbanion with 3 bonds and 1 lone pair is sp3 hybridized, as is this nitrogen with 4 bonds to other atoms. In this section, we talk about the bonding in ethylene, which has a carbon-carbon double bond. The hybridization changes to sp2. The Lewis structure of ethylene looks like both bonds in the double bond are identical. In fact, they are very different. For instance, one of the bonds is very reactive and the other is not. MO theory explains why. Experimentally, we know that ethylene is flat. MO theory also explains why this is so. As we mentioned in the VSEPR section, the bond angles are not exactly 120 degrees because the three groups attached to each carbon are not identical. The carbon in ethylene is sp2 hybridized. Starting from the original electronic configuration of carbon, we take the 2s orbital and only 2 of the 2p orbitals and hybridize, that is, mix them together, to form 3 new sp2 orbitals. We have a leftover p orbital, which we leave untouched. The sp2 orbitals are 33.3% s and 66.6% p character. They are identical and degenerate in energy. Notice that they are intermediate in energy between the starting 2s and 2p orbitals. These sp2 orbitals will be used to make 3 sigma bonds. The leftover p orbital will be used to make a new type of bond called the pi bond. Finally, we distribute 3 electrons to the 3 sp2 orbitals and 1 electron to the p orbital. We assume in this discussion that it costs less energy to put the 4th electron in the slightly higher energy p orbital than it costs to pair it in an sp2 orbital. In our analysis, we will show the sigma and pi framework separately. We will do this to make the bonding situation easier to see. In reality, they always exist together in the molecule and are superimposed on each other. In the sigma framework, each sp2 carbon is trigonal planar and will form 3 sigma bonds. Recall that sigma bonds have their electrons directly between the 2 atoms. The carbon-carbon sigma bond is made by sp2 overlap. The other sp2 orbitals overlap with the 1s atomic orbitals of hydrogen atoms to make 4 carbon-hydrogen sigma bonds. In the pi framework, the leftover p orbitals on each carbon overlap to form a new pi bond. In our drawing, we show the sigma bonds as lines to simplify this drawing. We draw the sigma bonds as a side-on view with hydrogens pointing forward and back. Then we draw the p orbitals and the resulting pi molecular orbital in the plane of the paper. This drawing clearly shows that the new pi bond is above and below the plane of the atoms, which is very important to know. We can draw the new pi bond by retaining the memory of the original p orbitals and just showing the overlap, or we can sketch in the actual shape of the new pi molecular orbitals. I like to use the first representation. Notice that the p orbitals must overlap with the same sign. The new pi molecular orbital also has opposite signs on each side, but this has nothing to do with where the electrons reside. The pi electrons reside equally well on the top or bottom. Overall, a double bond consists of 2 electrons in a sigma bond and 2 electrons in a pi bond for a total of 4 electrons. The pi electrons are quite different from the sigma electrons. They reside above and below the plane of the molecule. They are further away from the nuclei on average and so more loosely held than sigma electrons. We can say that double bonds have an electron-rich pi cloud. These loosely held pi electrons are reactive and tend to be given away to electron-seeking atoms or molecules such as H+. The arrow shows the electrons moving towards the H+. Sigma bonds are much less reactive because their electrons reside directly between the nuclei and are much more strongly held. How do you decide if an atom is sp2 hybridized? The rule is that any carbon, nitrogen, or oxygen with any combination of 3 bonded atoms and or lone pairs will be sp2 hybridized. This usually means that the carbon, nitrogen, or oxygen is in a double bond. Pause and try these sample problems. Identify the hybridization of each atom, except hydrogen, in the following molecules. Let's put in the hydrogens for benzene. You can see all the carbons have 3 atoms bonded, so they are all sp2 hybridized. Almost all carbons in double bonds are sp2 hybridized. In B, the carbon has 3 atoms bonded and is sp2 hybridized. The oxygen has 1 carbon atom and 2 lone pairs, and it too is sp2 hybridized. The CH3 has 4 atoms bonded, so it's sp3 hybridized. The molecule in C has a doubly bonded carbon, which is sp2 hybridized. The nitrogen has 1 lone pair, 1 hydrogen, and 1 carbon bonded, so it's sp2 hybridized too. This CH2 carbon and this CH3 are each tetravalent, so they must both be sp3 hybridized. The carbocation is a rare exception to the rule that sp2 atoms are always in double bonds. The carbon has 3 hydrogens bonded and is also sp2. In double bonds, the p orbitals must align perfectly for maximum overlap. This results in restricted rotation around the double carbon-carbon bond. In practice, there is no rotation around double bonds. It would cost 264 kilojoules per mole to break this bond, which is prohibitive. The result is that the 4 atoms attached to the double bond are held in a planar arrangement and they are locked into their positions. Because substituents on a double bond are locked into position, you can get cis-trans isomers, which are unique, non-interconvertible molecules. If 2 identical or nearly identical substituents are on the same side of the double bond, they are cis. If they are on opposite sides, they are trans. You can't have cis-trans isomers if you have the same groups on a single carbon. Cis-trans isomers are examples of a broader class of isomers called stereoisomers. These are non-interconvertible molecules which have the same order of connectivity of atoms, but which differ in the 3-dimensional arrangement of atoms. In topic 5.8, you can see all of the types of isomers we will study this semester. Finally, we talk about the bonding in acetylene, which has a carbon-carbon triple bond and is sp hybridized. Experimentally, acetylene is a linear molecule with 180-degree bond angles. It has 2 reactive pi bonds and 1 non-reactive sigma bond. We take the 2s orbital and only one of the 2p orbitals and hybridize them to form 2 sp orbitals. We leave untouched the leftover p orbitals. Note that sp orbitals are 50% s and 50% p in character. They are identical and degenerate. The sp orbitals are used to make sigma bonds. The leftover p orbitals are used to make 2 pi bonds. Finally, we distribute 2 electrons to each sp orbital and 2 electrons to each p orbital. In the sigma framework of acetylene, the carbon-carbon bond is made by overlap of 2 sp orbitals. The other sp orbital at each carbon overlaps with the 1s orbital of hydrogen to make a carbon-hydrogen bond. In the pi framework, the 2 leftover p orbitals at each carbon overlap to form 2 pi bonds. Note that the p orbitals are orthogonal to each other, and you would expect orthogonal molecular pi bonds. In practice, the 2 pi orbitals behave more like a cylinder or continuous cloud of 4 electrons, and you can draw the molecular orbital as more of a barrel shape. The triple bond has 2 electrons in a relatively unreactive sigma bond and 4 electrons in 2 reactive pi bonds. Recall pi bonds are electron-rich. Acetylene with 2 reactive pi bonds tends to react twice, when ethylene with only 1 reactive pi bond will react only once. How do you tell if an atom is sp hybridized? The rule is that a carbon, nitrogen, or oxygen with any combination of 2 bonded atoms and/or lone pairs around it will be sp hybridized. This usually means the atom will be in a triple bond. Here are some sample problems. Pause and try them. Identify the hybridization of each atom, except hydrogen, in the following molecules. In the first molecule, we find several types of hybridized orbitals. The CH3 group is sp3 hybridized. Both triple bond carbons are sp hybridized, and the double bond carbons are sp2 hybridized. In the molecule in B, the triple bonded nitrogen is sp hybridized. The nitrogen has a bond to a carbon and a lone pair as its 2 attached groups. The triply bonded carbon is also sp. The CH3 is, of course, sp3 hybridized. In carbon dioxide, the central atom is attached to 2 oxygens by double bonds and is sp hybridized. The double bonded oxygens are sp2 hybridized. The 2 pi systems of the attached double bonds are orthogonal to each other. That is, they are at right angles to each other because the 2 p atomic orbitals on the central carbon started out orthogonal. We need to briefly look at the bonding in benzene to understand what its true structure is and why it is so much less reactive than other molecules with carbon-carbon double bonds. We'll look at benzene's bonding in much more detail in second semester. The Lewis structure of benzene suggests that it has discrete single and double bonds. This is absolutely not true. In reality, all 6 carbon-carbon bonds in benzene are exactly equal and are 1.5 bonds in length. That is, they are all midway between a single and double bond. We can explain this by using a highly simplified molecular orbital argument. Each carbon in benzene is sp2 hybridized. Each carbon has a leftover p orbital. Instead of the p orbital making a pi bond with one of the carbons next to it, the p orbital interacts with both p orbitals on either side. The p orbitals form a continuous pi system, with the result that benzene has a continuous array of 6 pi electrons. The pi electrons are said to be delocalized over the entire ring. The delocalized electrons are suggested by this common representation of benzene, in which we put a circle in the hexagon to show the spread out pi electrons. When you can delocalize electrons, they become more stable and less reactive. The pi electrons of benzene are much less reactive than the pi electrons in the double bond of ethylene. When you see a regular double bond reacting in a molecule, you should assume that a benzene ring in the same molecule will not react at all. If you're using my book, I encourage you to do the extra test your knowledge problems for this topic, so you can be sure you really understand it. All the answers are at the back. This video is closely based on my first semester organic chemistry self-help book. The book is organized into standalone topics so you can quickly teach yourself a few troublesome topics. It's also logical and organized from beginning to end, so you can easily learn the whole semester if you need to. My self-help book is particularly valuable in difficult learning situations, but you can also use it to get an edge. If you want to learn more about my books and videos, how to get the books, or my future projects, go to rescueedu.com.